Welcome back, everyone, ready to deep dive into a new topic. This time we're tackling something that sounds a little intimidating. Hyperbolic functions.
They're really not as intimidating as they sound.
I'll take your word for it.
Yeah.
I have to admit, though, when I first heard hyperbolic functions, I definitely thought, okay, what is this, some kind of advanced math that I'm going to have to dust off my old textbooks to understand?
Yeah, no, I get it.
But I think our listeners are going to be surprised by just how cool and connected this area of math really is.
Absolutely. And what's so captivating about hyperbolic functions is their elegance.
Okay.
They have these beautiful relationships and symmetries, and they pop up in some really unexpected places.
So let's maybe start then with the basics for our listeners who maybe haven't encountered this concept before.
Sure.
We've got hyperbolic cosine, which is written as cosh,
Right.
and hyperbolic sine, which is written as sin.
Exactly.
And they sound a lot like our old friends from trigonometry.
They do.
Sine and cosine. And there's some interesting parallels there.
Yeah, one of the keys to understanding hyperbolic functions is to try to visualize them.
Right.
So imagine the graphs of like e to the x and e to the negative x, those classic exponential curves. If you were to take the average of those two curves at every single point, you'd get a new curve.
Okay.
And that curve is always above the line y1.
Okay.
That, my friend, is the graph of the hyperbolic cosine, or cosh x.
I'm picturing it now in my head, and it's pretty weird how averaging those exponentials creates this curve that never dips below 1.
Right.
A pretty big difference from regular cosine, which bounces between magnitude 1 and 1.
Huge difference.
Yeah.
Exactly. And that seemingly small distinction has huge implications.
Okay.
This property makes cosh x perfect for modeling things that have a minimum value, like, for example, the shape of a hanging cable.
Oh, okay.
You'll often see it pop up in engineering and physics when describing those kinds of curves. They're called catenaries.
So what about hyperbolic sine? Does it also have a cool graphical interpretation?
Absolutely. It's constructed in a similar way, but instead of averaging e to the x and e to the negative x, we average e to the x and negative e to the negative x.
Okay.
This gives us a curve that looks a bit like a stretched out S.
So they're both averaging exponentials.
Right.
But there's a slight twist for that sin x.
A slight twist, but those subtle differences make all the difference.
So,
For example, unlike its trigonometric counterpart, sin x is an odd function.
okay.
What's fascinating is how these functions mirror each other in their symmetry.
Okay.
So the hyperbolic cosine, or cosh x, is symmetrical across the y-axis, what we call an even function. On the other hand, sin x is symmetrical about the origin, making it an odd function.
Okay. I think I'm starting to get a feel for these hyperbolic functions. They're like the cool cousins of sine and cosine.
I like that.
But tell me, are there any secret handshakes in the world of hyperbolic functions? You know, like special identities that connect them?
You're speaking my language. Just like trigonometry has its Pythagorean identity. Hyperbolic functions have their own special relationship, and it's surprisingly similar.
Okay.
It goes like this: cosine x, sin x, 1. Notice the minus sign in there. That's the key difference from the Pythagorean identity we know and love.
So it's like the Pythagorean theorem took a detour through a funhouse mirror, and this is what came out the other side.
I like it.
It's really interesting to me how this identity with just a little sign flip hints at this whole different world of mathematical relationships.
Precisely. It highlights the interconnectedness of math.
Yeah.
And speaking of connections, let's dive into inverses.
Okay.
Remember how every trigonometric function has an inverse?
Right.
Well, hyperbolic functions are no different.
Yeah, okay.
We have arc cosh x and arc sin x.
Inverses always feel a bit like undoing a magic trick.
Right.
Like, how did we even get here?
Right.
But there's usually some catch, right?
There is. Because cosh is always greater than or equal to 1, its inverse arc cosh requires a bit of a rule change. We have to restrict the domain of cosh x to x greater than or equal to 0
Okay.
to make sure it has a well-defined inverse.
It's like saying, okay, cosh x, you can come to the inverse party, but only the values of x that are 0 or greater are allowed.
Exactly.
I'm curious, though, what do these inverse functions actually look like? Are they as elegant as their hyperbolic counterparts?
You're going to love this. The inverse hyperbolic cosine, or arc x, can actually be expressed using a natural logarithm,
Okay.
ln x plus x cos 1, where x is greater than or equal to 1.
Whoa, logarithms are entering the chat. I was not expecting them to show up here.
Right.
It's amazing how these seemingly different areas of math often find a way to connect.
I know, and here's another fascinating connection. Remember earlier when we calculated the x-coordinate, or sin x equals 1?
Yes.
The value we found was ln1 plus su, which is the same value that appears inside that our cosh x expression.
Yeah.
It's a subtle hint at the deep relationship between these functions.
We've explored these fascinating relationships and even dabbled a bit in inverses, but now I'm ready to take it up a notch.
Okay.
What happens when we introduce calculus into the mix?
Oh, things get really interesting.
Are we about to uncover some wild derivatives?
Hold on to your hats, because the world of hyperbolic functions gets even more elegant when calculus comes into play. Remember how we talked about cosh x and the sin x mirroring each other in the symmetries? Well, that beautiful relationship extends to their derivatives as well.
Okay, you've piqued my curiosity, spill the mathematical tea. What's so special about their derivatives?
The derivative of cosh x is simply sin, and the derivative of sin x is cosh x.
Wow, so they just keep switching places.
They just keep switching places.
But it makes you wonder, why are their derivatives so intertwined?
That's the beauty of mathematics, uncovering these unexpected connections. This elegant back and forth hints at a deeper relationship between these functions, a relationship that becomes even more apparent when we explore them in the context of calculus.
Speaking of connections, what are the derivatives of their inverses? Do they hold any surprises?
The inverse hyperbolic functions also have some intriguing derivatives. For instance, the derivative of arcsinic x is 1 divided by the square root of xx plus 1. You'll often see this derivative pop up in calculus problems, especially those involving integrals.
I'm noticing a bit of a theme here with the square roots. It makes me think back to our earlier discussion about areas and how we used a trigonometric substitution with the square root to connect everything back to logarithms. Is there something inherently geometric about these hyperbolic functions?
You're right on the mark. There's a beautiful geometric connection, and that example you just mentioned perfectly illustrates it when we use that clever substitution replacing x with cos. We're essentially creating a bridge between the world of trigonometric functions, which are all about circles, and the world of hyperbolic functions. And as we saw, that bridge leads us to the natural logarithm, highlighting the interconnectedness of these seemingly different concepts.
This entire deep dive has been a web of interconnectedness. We started with these exotic-sounding functions and uncovered symmetries, secret identities, and even links to logarithms and geometry.
Yeah.
I have to ask, though, is there even more to discover?
There's always more to explore. Remember how we talked about trigonometric functions having a beautiful geometric interpretation with the unit circle? It makes you wonder, could there be a deeper, perhaps even more profound geometric interpretation of the relationship between cos x and the hyperbola? That's something for you to ponder as you continue your mathematical journey.
This has been one mind-bending deep dive.
Yeah.
I think I need to go for a walk now and contemplate all these incredible connections until next time.